Good evening, Internet. I'm Matt Booyak, and today I'm going to be solving the third problem in the projecteuler.net problem archive. So we'll see the problem description here. We have this large number, roughly 600 billion, and we're asked to find the largest prime factor of this number. So unlike the previous two problems that we've solved, this number really isn't amenable to classical analysis. We're really going to need some computer assistance. And so let's think about a basic algorithm that we might use to solve this problem. We could imagine that we have a list of all the prime numbers, and we start with the first one, 2, and then consider 3, 5, 7, etc., trying each prime number and noting which divide our number here. And eventually we'll come to a prime number that's larger than our number, and we know that at that point the last prime number divisor that we found is our answer. That seems like a very reasonable approach, and that algorithm would be correct. But if you were to describe that algorithm to an experienced software engineer, they would almost immediately be able to tell you that that's not going to be viable. And to understand how they would be able to make that determination so quickly and why they would make that determination, we have to talk a little bit about how computer scientists think about the analysis of algorithms and algorithm performance. So there's a broad class of computer science that deals with this analysis of algorithms. And so I'm just going to be touching the surface. But the basic question that you want to ask is, how does my algorithm behave when you double the size of the input? So it might be that when you double the size of the input, it also doubles the running time. And in that case, we would call that a linear or order n algorithm. That's actually, in most cases, that's the best that you can hope for. That's a pretty efficient algorithm. Now, instead, you might have an algorithm that you double the input size, and the result is that you quadruple the running time. And that we would call an order n squared algorithm. And there are many other classes of algorithms. You get into probabilistic polynomial and non-deterministic polynomial. There's this entire zoo of algorithms. But for day-to-day software engineering, there's really a small number of types of algorithms in terms of running times that you're going to encounter on a daily basis. There are the two that I just mentioned, and then also exponential and n log n are fairly common, certainly worth being aware of. And I won't touch on those in this video, but I expect I'll get to those in a future video. So the reason that it's important to know the distinction between an order n algorithm and an order n squared algorithm is that if you think about an input of size 100 million or even a billion, on a modern workstation, if your algorithm is order n, you're going to be able to chew through that pretty quickly and get your answer in a reasonable amount of time. But with an order n squared algorithm, even a modest input size of 100,000 or a million, you're going to be waiting quite a while, potentially hours or days, to get your answer back. And so the reason why, and I said that an experienced software engineer would be able to recognize the problems in the basic algorithm I described, is because generating primes is order n squared. And so they would recognize that, they would see the size of our input, and they would probably decide that that wasn't going to be a viable solution. So we're going to have to find something a little bit more clever in order to solve this problem. So the first observation that we might make is that while determining the largest prime divisor is maybe non-trivial, determining the smallest prime divisor is actually pretty straightforward. And that's because the smallest prime divisor is also the smallest divisor of any kind, other than 1. We're not counting 1. And so we can just start off with 2, 3, 4, 5, 6, 7. We don't even have to be concerned that we're trying numbers that aren't primes. We can just try each of the numbers until we find a divisor, and we know that that's the smallest prime divisor. Now the second observation that's going to help us out here is that when we find the smallest prime divisor, if we divide our number by that prime, we get another number that has the same largest prime divisor. And so let me just show you what I mean by that using their example input here. So they give 13,195 as an example input, and it has the factors 5, 7, 13, and 29. And we don't know, what those are off the bat. We're just given this number. But we start searching, and we find that 5 is a prime divisor. And so, we take 13,195, we divide that by 5, and we get 2,639. And we don't know what the largest prime divisor is, but even without knowing what it is, we know that it must divide both our original number, 13,195, and this new number, 2,639. And so this is a very common theme in the design of algorithms, where you try to transform your problem into a simpler problem that has the same answer. And you can continue that process until you get to a problem that's simple enough that it can be solved trivially. So in our case, we might continue this process of finding the smallest prime divisor and dividing until we get just a single prime number remaining. And in that case, we know that that's our answer. Now, one final point of concern is that when you're analyzing algorithms, we like to look at what's going to happen in the worst case scenario. And so we might imagine the worst case scenario for our number is if this were prime, then we would have to search all the way up to 600 billion in order to determine that it's prime and that this is our answer. But as I was saying, even with a linear time algorithm, once you start to get into the tens of billions, hundreds of billions, trillions for your input size, again, you're going to be waiting possibly hours or days or even longer. Now, fortunately, there's a trick we can use to determine whether our number is prime or not, without having to search all the way up to our number itself. And that's because the factors of a number will come in pairs, where one number in the factor pair is going to be less than the square root, and the other is going to be greater than the square root. So, for example, let's take just the number 10. So if we take the square root of 10, you can see it's between 3 and 4. And as an example of a factor pair, you have 2 times 5 is equal to 10. And you'll notice that one of those, 2, is less than the square root of 10, and the other is greater than the square root of 10. So if we're trying to find factors of our number, we don't have to search all the way up to our number. We only have to search up to the square root of our number. And if we get up to the square root of our number and we haven't found any divisors, then we know that our number is prime. So that's the final optimization that's going to let us solve this problem. So let's get into writing some code. Let's see, so we'll go over here, open up Emacs, open up a shell. I want to apologize briefly. I noticed that in the previous 2 videos you weren't able to see any of that stuff. So we're going to start my my terminal down here now. I apologize for that mistake. But let's make a copy of our template directory. We'll call that problem 003. And let's go over here and open up our main.cpp. Okay, so we're going to want a let's see here. First, have our input. Call that n. Copy that over from the problem statement here. And let's see. So we're going to want to keep track of our current divisor that we're trying. So, oh, and actually, I've already made a slight mistake here. We're going to want to modify our n as the program runs, so we don't want that to be constant. We'll just call this div. And so we'll say div is going to start off at 2, and it's going to run as long as div times div is less than n. So this is a little trick. Computing the square root is computationally expensive, and you get floating point numbers involved. But it's easy to just square two integers, or sorry, multiply two integers together to square this number. Is much more efficient. And let's actually make our div here also 32-bit or 64-bit integer. That was a minor mistake there. And then we'll just increment div. And then we'll say if we have n mod div is equal to 0. So this is as I explained in the first video that I did, this is just checking to see if n is divisible by div. And if it is, we want to say n divide equals div. So that's going to say, this is equivalent to saying n is equal to n divided by div. And there's one point of caution here where we might actually have the same prime factor multiple times. You could imagine the number 12 is equal to 2 times 2 times 3. So we would try 2, we divide it by 2, we get 6. If we're not careful and we move on to trying 3 next, we would miss that there's that other factor of 2. And so what we want to do is use a continue statement here. So this will skip over incrementing div, and we'll try that same. Oh, excuse me. I've structured my loop incorrectly here. Let me make a few corrections. So I've used a for loop here, but we actually want to use in order for this to work correctly, we should use a while loop. And so what this will do, this will actually do what I was describing. And so yeah, now when we do this continue statement, that means that we will do this check, and then we will try the same divisor again rather than continuing on to the next divisor. And so when we get down to the end here, n should be the value of the largest prime divisor. So then we're going to say printf, and we'll say largest prime divisor is equal to n. And before we try this on our large number here, just as a sanity check, it's always a good idea to try it with the test input that they give you, just to make sure that you haven't made any mistakes. And in a real software engineering setting, obviously you're not going to be given this test input, so you might have to go and calculate your own test inputs to determine whether your program is behaving correctly, or at least give some basic sanity check as to whether your program is behaving correctly here. So let's see, we'll do 64t, n is equal to our smaller number here, and we'll just comment out our real number there. So now let's go back over here, go into our problem directory, build that, and we'll give that a shot. Okay, so it says largest prime divisor is 29. Okay, that's promising. And so now let's try it for real. Let's go back over here. All right, so it says our largest prime divisor is 6,857. So you know, this program is pretty simple. We probably didn't make a mistake, but as long as we can double check our work, you should always double check your work. So let's go over here and go to our analysis, and let's just grab this number. And we're going to say that that's equal to 6,857 times. So we're going to say 600,851, 475, 143 divided by 6,857. Okay, so that gives us this other number here. Oh, that didn't work. There we go. But now we can continue to break this down. And okay, so now it says the next largest prime divisor is 1,471. So we'll go over here. We'll say this divided by 1,471. So this is just providing some basic checks that our number actually is divisible by these factors. And then when we're done with this process, we'll be able to multiply them together and see that indeed this is a factorization of our original number. We still won't know for certain that these numbers are prime, but it'll give us some basic confidence that we didn't make some simple mistake. Okay, so now we have 1,471 times this number here. $839. Okay, so we say divided by 839, and that gives us 71. And I believe 71 is prime. Yes. And in fact, we can check that really quick. Okay, so we have 71. Let's see, we have 71 times 839 times 1,471 times 6,857. So that's 600,851,000,000. 475,143, which is our original number. So our answer is 6,857. So we can go back here to the archives, and we can go to the third problem, and see that that is indeed our answer. So in the next problem, we will continue with Project Euler problem number 4.